Friends, myself, Thomas Methew, from Gujarat National Law University, Gandhinagar, which is the only national law school of India that offers an integrated BSc LLB program at the undergraduate level. It's my pleasure to be part of this second online refresher course in physics being organized by the UGC Human Resource Development Center of Gujarat University, Ahmedabad. I'm thankful to Professor P.N. Gajjarji and Dr. M. Boraji and the Department of Physics, Gujarat University, for providing me with this opportunity. The title of my talk is Nuclear Technology in India, Scientific and Legal Dimensions. The personality whose photograph is there on the screen, I'm sure that all of you are aware of. He is Homi Jahangir Baba, who is considered as the father figure for the nuclear science program in India. I'm sure that all of you might have come across such news articles. A nuclear blast which took place in the nuclear reactor at Japan. People affected by the radiation in the Mayapuri region. Protests going on in different states of India with regard to the construction of nuclear power plant. This necessitates the need to understand the scientific as well as the legal dimensions. And so this talk. When we talk about science and law, Sri P. M. Bakshi, former member, Law Commission of India, had said, if science is the accumulated knowledge of centuries, law can be rightly described as collected wisdom of the ages. Knowledge of the material world, its purest form is science, and when put to practical use, it becomes technology. Wisdom at the peak of its excellence is the foundation of the ideal political system, and when utilized to regulate human relationships, becomes the law. It's very important to understand the contact point of science and law. And it can be seen that any development in either of the fields, be it science or law, necessitates modification in the other to suit the development which has been made. And so it's very important to understand or have an idea of both the scientific as well as the legal aspects. Let's first deal with the scientific aspect. Atomic number. Atomic number is basically the number of protons. And if it's a stable atom, it is also basically equal to the number of electrons. And it is denoted by Z. It is written on the lower side of the symbol of the element. The next is the mass number, which is equal to the total sum of number of protons and the number of neutrons. And if it's a stable atom, it is also equal to the number of electrons plus the number of neutrons. It is denoted by A, and it is written on the upper side of the symbol of the element. And so, if X is considered to be the symbol for the element, it is represented by XAZ. In nature, if we observe, it can be seen that there are certain nuclides with same atomic number, but different number of neutrons. And these are known as isotopes of each other. One of the examples is H11, H21, H31, which is there on the screen. And these are basically considered as the isotopes of hydrogen, protium, deuterium, and tritium. Isotopes of an element have identical electronic structure and hence the same chemical properties. In nature, there are certain nuclides with same mass number, and these are known as isobars. And the example is H31 and He32. It can also be seen that there are certain nuclides with same number of neutrons but different atomic number, and these are known as isotones. One of the examples is Hg 19880 and Au 19779. Seeing all these things, it can be understood that it is very important to understand the size of the nucleus. However, if we observe, it can be seen that the nucleus is not a solid object and does not have any sharp boundary. However, we can still assign a size to the nucleus. The size and structure can be learned by bombarding them with a beam of energetic probe particles and observing how the nuclei deflects the incident particles. I'm sure that all of you have heard of the famous Rutherford experiment. Now, the effective radius of a nucleus is given by R is equal to R0, A to the power 1 by 3, where A is mass number and R0 is a constant, which is of the order of the range of nuclear force. The value of R0 depends on the probe particles, and the volume of the nucleus is directly proportional to A and is independent of separate values of number of neutrons and atomic number. Now let's look into the peculiar nature of the nucleus. We know that the nucleus is made up of protons and neutrons, and therefore there can be an expectation that the mass of the nucleus has to be equal to the total mass of its individual protons and neutrons. However, if we observe, it is not the case. The nuclear mass is always less than the total mass of its individual protons and neutrons. And this difference in the mass of the nucleus and its constituents is known as the mass defect. Einstein, who is famous for giving this expression of delta EB is equal to mc square, found that the difference in the mass is there in terms of the energy. And this delta EB is basically the binding energy of the nucleus, which binds the nucleus in its state. Because what is happening is protons which are positively charged in nature, they already have electrostatic force between them, which is very powerful and repulsive in nature because of the similar charge. And then also they are bound within the nucleus, which shows that there has to be some more powerful force, which is a strong nuclear force, which binds it. So we can see that the mass as well as the force makes the nucleus a very interesting point of study. This personality, whose photograph is there on the screen, I'm sure that all of you are aware of, is Antoine Henry Becquerel, who basically discovered the phenomenon of radioactivity in the year 1896. The phenomenon of emission of active radiations from certain substances is called radioactivity. The substances which emit such radiations are called radioactive substances. And in nature, we can see that uranium, radium, thorium, and plutonium are some of the examples of radioactive substances. In general, if we observe, there are three types of radiations which are released: alpha, beta particles, and gamma rays. So let's look into the characteristics of these. Alpha particles are regarded as helium nuclei, that is He2+, whereas beta is regarded as the electrons, and gamma rays are regarded as the electromagnetic radiations. The mass of the alpha particle is 4 AMU, atomic mass unit, whereas beta and gamma are basically negligible. When we look from the charge perspective, it can be seen that the alpha particles has +2 units, whereas beta has -1 unit, whereas the gamma doesn't have any charge. The speed of alpha particles is about 1/10th of the speed of the light, whereas the beta and the gamma, they have the speed same as that of light. The penetration power of alpha particles is the least, whereas that of beta is medium, and the highest penetration power is possessed by the gamma rays. The representation of alpha particle is He2+, and beta particles is E0-1, whereas gamma is gamma 00. Now let's look into the nuclear reactions. These are basically those reactions in which the nuclei of the atoms undergo change, forming new atoms and releasing tremendous amount of energy. The nuclear reactions can be classified into two categories: nuclear fusion reaction and nuclear fission reaction. The nuclear fusion reaction is basically a process in which two or more nuclei of lighter atoms combine to form a heavy nucleus with the liberation of a large amount of energy. And one of the reactions which is there on the screen is H21 plus H21 forming helium He42 plus release of tremendous energy. This is also known as thermonuclear reaction. Now let's see what is a nuclear fission reaction. It is basically a process of splitting of a nucleus of a heavy atom into a number of nuclei of smaller mass with the liberation of large amount of energy. And the best known reaction is basically the uranium-235-92 when bombarded with a neutron N10 releases barium and krypton along with the release of 3 neutrons and tremendous amount of energy. Now let's see what is the difference between a nuclear fission and a nuclear fusion. We have already seen that fission is basically splitting of nucleus of a heavy atom into a number of nuclei of smaller mass. On the contrary, fusion is basically combining of two or more lighter nuclei to form a heavy nucleus. The fusion liberates very high energy in comparison to the fission reaction. And also, the temperature and pressure that is required for fusion to take place is also very, very high in comparison to fission. In fission, what happens is there is release of harmful radiations as a byproduct, whereas in fusion, such harmful radiations are not released. The fission also requires a high energy particle for initiation of the reaction, whereas fusion doesn't require any such particle. The fission reaction is basically in the form of a chain reaction. I'll be explaining what is a chain reaction. However, fusion is not in the form of a chain reaction. The fission, it can be observed that can be controlled because it requires basically a high energy particle for initiation of the reaction. Whereas on the contrary, in case of fusion, first of all, it has not been conducted under the lab conditions. And even if it's conducted, there is a question mark on how to control the same because there is no high energy particle involved in the initiation of the reaction. The fission reaction are of two types because we'll focus on fission reaction because it has been undertaken under the lab conditions. It can be divided into two types. Uncontrolled fission reaction. This is also known as explosive fission reaction. In this, what happens is the number of atoms undergoing fission is not under control, which can be seen in, say, nuclear bombs. The second category is controlled fission reaction, which is also known as critical fission reaction. In this case, the number of atoms undergoing the fission is under control, like say a nuclear reactor. On the figure, there is a diagram which highlights the chain reaction. Now here, if we observe, it can be seen that a neutron is bombarded on the uranium nuclei and it generates the krypton and barium, which results also into generation of 3 more neutrons. And these 3 neutrons can further contribute towards the fission reaction and it goes on. And so this is a chain reaction. In turn, we can say that it is a reaction in which the particle that initiates the reaction is produced during the reaction so that the process may be repeated again and again. Now, let's look into the critical mass, which is very important parameter. It is basically the minimum amount of fissionable substance required so as to continue the chain reaction under given set of conditions. Now, the reaction is undertaken under a specific setup or arrangement, and this setup is known as a nuclear reactor. And the nuclear reactor has several important parts like nuclear fuel, control rods, moderator, coolant, and shield. Now let's look into these components. Nuclear fuel, it is basically consisting of the fissionable material, like say for example enriched uranium-235. Then we have control rods. These are basically the rods which are used to absorb the neutrons. In turn, you can say that to control the reaction. And boron or cadmium are being used as the control rods. The next part is basically a moderator. It is basically used to slow down the neutrons, and it does not remove the neutrons. The graphite and heavy water are generally used as the moderators. Then we have a coolant. It is basically required to absorb the excess heat, or we can say that to maintain the temperature of the reactor. The examples are liquid sodium or heavy water. Then we have a shield, which is made up of steel and lead, because when nuclear reaction, especially the fission reaction, is going to take place, harmful radiations are going to be released, and it should not be released into the vicinity. And so we need to have a good shield which can absorb if any is being released. Now let's look into a nuclear reactor. This is a basic diagram of a nuclear reactor. Now here, this particular section is basically the shield. Then we have these bars, which are basically the fuel rods. Then we have two more, which are control rods. And if we observe, it can be seen that the control rods are placed in between the fuel rods, so that it can be used up to ensure the rate of reaction takes place as required. The dots which are there in between, this one is basically for the heavy water reactor, and so the coolant and the moderator are the same. So these dots are basically representing the heavy water. Then you have a heat exchanger section. Then you have a turbine. You have a generator. You have a condenser. Now, what is happening is, let's look into the working. When the fuel rods are bombarded with high energy neutron, the fission reaction starts. And depending upon the insertion of the control rods, the rate of reaction will continue. If the rods are fully inserted between the fuel rods, the rate of reaction will stop. Now this way the reaction is continuing. Because of the reaction, energy is being liberated, and the coolant which is there is basically absorbing the heat. That coolant is passed through the pipeline into the heat exchanger. And here what happens is, the water is present in the heat exchanger, which gets converted into steam, and that steam is basically used to rotate the turbine, and in turn it helps in generating the electricity. Once the steam is being used for generation of electricity, its energy is lost, and so it is passed through a condenser section so that it can be converted into liquid state again, and that liquid is again pumped into the heat exchanger, so that there is no wastage of water for this purpose. When we look into a reactor, there are certain difficulties also associated with its working, like say neutron leakage. However, it can be ensured that this problem is taken care of by making the core large, in turn reducing the surface to volume ratio. The next is the neutron energy. The neutrons, when they are moving, the kinetic energy is associated with them. And if they possess higher energy, it is of no use. And if they possess lower energy, it is also of no use. And so there is an optimum value. And when the neutrons acquire that optimum value, which can help in fission reaction to take place, they are known as the thermal neutrons. Neutron capture. Sometimes what happens is, the neutrons are being captured by the nuclei, but it doesn't result into a fission reaction. And such capture is of no use. It basically is going to impact the efficiency of the reactor. And such capture is known as non-fission capture. Now let's look into the different types of nuclear reactions. I'm sure that everyone is aware of the reaction which is shown on the screen. See, what is happening is, here if we observe, there are two capital alphabets and two small alphabets. The small ones are written between the bracket. Now let me explain what they represent. This one is basically the target nucleus. This one represents the product nucleus. And this one represents basically the projectile particle. And this one represents the ejected particle after the reaction. Now see, the first reaction is basically elastic scattering. Now from the elastic scattering, we know that what is going to happen. And so what happens is, the target nucleus as well as the product nucleus is the same. And even the projectile particle as well as the ejected particle also is going to remain the same. And that's why the expression is x within bracket, two small x's and capital X outside. Then comes the elastic scattering, inelastic scattering. Now here what happens is, when a projectile particle is bombarded on the target nucleus, what happens is, it does releases a ejected particle Y, and release of Y makes the product nuclei, which is of the same nature as that of the target nuclei but in excited state, and that's why the symbol star is shown here. The next one is the radiative capture. In this, what is happening is, again we are bombarding a particle over the target nuclei. However, because of this, what is happening is, the gamma rays are being released as the ejected particle, which makes that a product nuclei is being created, but it is in excited state, and generally it is basically the compound nucleus. Now let's see the disintegration process. This is like a general reaction wherein what is happening is, a particle is bombarded over the target nucleus, which results into generation of a product nuclei which is totally different than the target nucleus, as well as ejected particle which is also different than the incident particle. Now let's see the many body reaction, which is also sometimes known as the spallation reaction. Now here what is happening is, you do bombard on a target nuclei with a particle, the projectile particle, and it results into release of many ejected particles, and that's why Y1, Y2, Y3 has been shown, along with the generation of a product nuclei which is different than the target nuclei. Now the next one is basically the photo disintegration process, wherein what is happening is, the gamma is being used to bombard the target nuclei, and it results into generation of a product nuclei which is different than the target nuclei, and also release of a ejected particle. The nuclear fission reaction, since we have already seen the example, I am not repeating it again. Elementary particle reactions. Now these are the ones in which what is happening is, the elementary particles are involved as a projectile particle or as an ejected particle. The next one is heavy ion reaction. In these, what is happening is, the projectiles which are being used are heavier than the alpha particles. Now let's see the different types of nuclear reactor. But before going to the different types, let me share that the nuclear reactors can be, first of all, categorized based on different criterions, and under each criterion we can have different types of reactors. So the first criterion is basically distribution of fuel and moderator, and based on that, the two types of nuclear reactors are One, the homogeneous reactor, wherein the fuel and moderator are intimately mixed in the form of a solution or slurry. Whereas the second one is heterogeneous reactor, wherein the lumps or rods of uranium are arranged in a lattice within the body of the moderator. The heterogeneous reactor has one advantage, that the resonance neutrons are almost completely absorbed in the outer layers of the uranium lumps. Now let's look into the different types of nuclear reactor based on the purpose for which it is being used. The first one is the research and development reactor. From the name itself, it's clear that it is going to be used to test new methods of reactor design. It can also be used for supply neutron beams for physical, chemical, and biological research, or it can also be used for radioisotope productions. There are 5 main groups under this category. I won't be explaining all the 5 groups, but I will just share the names because name itself gives an idea. The first one is natural uranium graphite. The next one is natural uranium heavy water. The next one is enriched uranium heavy water. The next one is homogeneous enriched uranium ordinary water, which is also known as water boiler. Then we have heterogeneous enriched uranium ordinary water, which is basically a swimming pool or MTR. Then comes the pulsed reactor. Based on the purpose, the second type is basically the production reactor. We know that uranium-235 is only fissionable species occurring in nature which can be used. And for generation of huge amount of electricity, there is a burden to have the fissionable species in sufficient quantity. So uranium-238 and thorium-232 can be converted into fissionable Pu-239 and U-233 respectively. And such reactors are basically known as the production reactors. Then we have the breeder reactor. See, what is happening is, in production reactor, the quantum of the fissionable material that is being produced is in a limited manner. Whereas in breeder reactor, what is happening is more fissionable fuel from fertile materials than is being consumed for operation of a reactor are being generated. The breeder reactors can be of 2 types, thermal as well as fast, based on the neutrons and its characteristics. And it has been observed that breeding is more probable with fast neutrons than with thermal neutrons. The last type is basically the power reactor. From the name itself, it's clear that the main purpose of it is to generate the power. And it can have 2 categories. The first one is the mobile reactor, which are generally used in aircraft, submarines, or ships, which basically helps it to make the movement of the bodies of ships or submarines. The next one is stationary reactors, which are generally used for generation of electricity. Now, the types of nuclear reactors based on the purpose under the category of power reactor also has several types. The first one is basically the pressurized water reactor, which is in short known as PWR. In this, what is happening is the water under high pressure is used both as moderator and coolant. The next one is boiling water reactor. In this, the steam is directly fed from the reactor to the turbine. The next one is the homogeneous reactor, which I have already shared, so I won't discuss. Then the breeder power reactor also has been discussed. The next one is the organic moderator reactor. In this, the organic liquid is being used, which has generally high hydrogen content and which results into a high boiling point at atmospheric pressure. The last one is basically the gas-cooled reactor, wherein the gaseous coolants are being used, like say for example carbon dioxide or the helium. So gas-cooled graphite moderator reactor. Now let's look into the wastes. And what is happening is there are different types of sources of nuclear waste. The first one is basically the uranium production, wherein there are two ways. One is mining and the other one is the milling. Mining, we know that, is basically the extraction process which is undertaken. And milling is basically the mill tailings, wherein the radioactive sand-like materials that remain after the uranium is extracted. Then is basically the operation of nuclear reactors. We all know that whenever a nuclear reactor is operated, there are going to be left out certain waste, like say for example barium and krypton, which are being released, and other materials. Then the fuel fabrication. See, the fuel rods have to be of a specific dimension so as to ensure proper absorption of the neutrons and proper efficiency of the reactor. So when the fabrication of the fuel is being made, it is obvious that there are going to be certain materials being taken out. So that acts as the waste. The next one is the reprocessing. The waste generated from reprocessing of a nuclear fuel or the spent fuel is highly radioactive, and it emits significant radiation and heat and is transferred to a fuel pool for several years before being transferred to interim storage facilities. The next one is manufacture and maintenance of nuclear weapons, which also produces waste which is known as transuranic waste, that is TRU. And the last one is decommissioning of nuclear power plants. I'm sure that right now all of you might have heard of the news wherein the Russia-Ukraine war has been there, being told on a daily basis. The Russian forces basically, first of all, took where their focus was the Chernobyl site. And we know that the nuclear blast had taken place there. Now, when the Russian forces captured that site, we have heard that still the release of the radioactive substance or the impact of the radioactive substances can be felt, the radiations can be felt. So it shows how strong it could be. The next one is basically the categories of the waste. The first one is high level waste, which is also known as HLW. Now, this results from spent nuclear fuel used by power reactors to produce electricity, and which is generally part of the civilian nuclear programs. Then we have transuranic waste, that is TRU, which is also sometimes known as the legal waste, and it results from the defense program or the nuclear weapons. Then we have uranium mill tailing waste, which results from commercial uranium ore processing activities, which are being followed after the mining. Then we have low level waste, which are basically due to the reactor operations and from areas like, say, for example, medical, academic, industrial, etc., and contain relatively limited concentration of radioactivity. Then the decommissioning waste, we have already seen about the decommissioning aspect. It results from the decontamination and removal of radioactive materials encountered during site closure and restoration activities. And the last one is the exempt waste, which generally meets the criteria for clearance and exemption from regulatory control for radiation protection purposes. Now let's see the management of the nuclear waste. See, what is happening is the management of the nuclear waste mainly rests with each state that produces such waste. However, the spent fuel, if being transferred for processing in another country, the residual waste is generally returned to the originating country for its long-term management. In general, if we observe, it can be seen that the radioactive waste from nuclear power plants are stored at the site itself. There are several mechanisms which are being used to dispose of the nuclear waste. Like, say, for example, the nuclear waste was dumped in the sea during 1960s and 1970s, which resulted into a huge problem being faced by the shore regions. The geological disposal of high-level radioactive waste in an underground repository is favored by many countries. And if we look into, the Finland is the only country, or it initiated basically in the year 1987 by its Nuclear Energy Act, which stated that the permanent disposal of the spent nuclear fuel shall be ensured. Now let's look into the other use of the nuclear technology. Till now we have focused on the peaceful uses. That is now the weapons. Now let's first of all understand what is the difference between a nuclear weapon and a conventional weapon. In nuclear weapon, the reaction which is going to be used is a nuclear reaction. Whereas in a conventional one, it is basically the chemical reaction that is going to be used up. The energy which is going to be liberated in a nuclear weapon is going to be of very high magnitude compared to the conventional one. The conventional weapon doesn't release harmful radioactive radiations, whereas nuclear weapon does release the harmful radioactive radiations. The conventional weapon has a destructive power, but it is very less compared to the nuclear weapon. When we look into the recovery time that is taken after an attack by a nuclear weapon, it is very, very huge in comparison to the conventional one. The conventional one is easy to manufacture and store in comparison to the nuclear weapons. And the material that is being used is gunpowder, whereas for nuclear weapon, it is basically a fissionable material like say uranium and fusible material like say hydrogen. Now let's look into the classes of nuclear weapons. The first one is basically the tactical weapon. These are basically meant to be used in the battlefield against military formations and are typically low-yield weapons. The second is basically a strategic weapon, which are basically high-yield weapons and designed to kill civilian population in cities. There are different types of nuclear weapons. The first one is pure fission weapon. From the name itself, it's clear that it is basically the fission reaction which is going to be responsible for the functioning of the pure fission weapon. And that's why it is also sometimes known as simple fission weapons. And the example is atom bomb. The simplest nuclear weapons are these to be designed and built. And they form the basis for developing other types of nuclear weapons. These can be used both as tactical as well as strategic weapons. The next one is basically the boosted fission weapon. Now, if we see the diagram here, we have fissionable material as well as fusible material in this particular weapon. The only thing is the fissionable material is in larger quantity compared to the fusible material. And what happens is the fission reaction starts because it doesn't require that much high pressure and temperature as compared to the fusible material. However, because of the fission reaction, the temperature and the pressure condition increases, which results into the fusion reaction to get started. And once the fusion starts, the temperature and pressure increases tremendously. And that basically helps in increasing the rate at which the fission can further take place, in turn enhancing the power of the weapon. And that's why it is known as boosted fission weapon. The next is thermonuclear weapon. Now this also has the fusible material as well as the fissionable material. The only difference is here the fusible material is in larger quantum compared to the fissionable material. The fusion as such directly cannot take place. So the fission reaction starts, which results into the increase in the temperature and pressure, and which in turn initiates the fusion reaction. And that fusion reaction keeps on continuing, resulting into a huge quantum of energy being liberated. And one of the example of this is the hydrogen bomb. You can further incorporate a third fission stage if the power has to be increased further. The next type is enhanced radiation weapon. These are also known as neutron bombs. These are basically small thermonuclear weapons which are designed to produce intense nuclear radiation. And these are basically tactical weapons designed to kill soldiers protected by armor. For example, inside the tanks. The radiation produced by the neutron bombs can easily penetrate the armor of tanks and kill the humans who are there inside. The next one is basically salted nuclear weapon, which is also known as cobalt bombs. These are thermonuclear bombs which are designed to produce large amount of long lasting radioactive fallout. And if there is a fallout that is more intense and lasts much longer than, say, unsalted weapons, that is going to create havoc. And that's why these devices are also known as doomsday devices, since they have the capacity to kill everyone on the earth. These weapons have not been built or tested till now, but as we know that several things are kept secret too. Types of nuclear weapons. In this, the last category is pure fusion weapon. From the name itself is clear, the pure fusion will have only the fusion reaction. Till now, it has not been achieved, but yes, research is going on and there is a good probability that this could also be achieved. On the screen, the figures which are there, the photographs which are there, I'm sure that all of you might have seen these photographs. These are basically known as the mushroom clouds because it resembles the shape of a mushroom. And these are basically because of a nuclear explosion. Now let's see the effects of nuclear weapon. The effects can be divided into two categories. The first one being the direct effect, and the second one is the indirect effect. Under the direct effect, we can have the blast wave, the thermal radiation, which is also known as the heat radiation, and the last one is the nuclear radiation. And if you observe the direct effect, the blast wave basically comprises the 50% of the direct effect, and thermal radiation just comprises the 35%, and the nuclear radiation is merely 15%. Under the indirect effect, we have electromagnetic effect and the effect on climate. Now let's see each one. The blast wave. Let's take an example of a 15 kiloton range weapon. When such a weapon is exploded, the blast wave travels faster than the speed of the sound, and within the 1.2 kilometer, it can be observed that the wind speed is in excess of 800 kilometers per hour, and the pressure is in excess of 10 psi, that is pounds per square inch, and the most buildings are going to be demolished. Between 1.2 to 2.5 kilometer, the pressure is 3 psi, and the wind speed is about 150 kilometers per hour. Though it has reduced, the injuries on a large scale can be caused, as well as fatalities can be there. Beyond 2.5 kilometer, the pressure drops to less than 1 psi. And because of this, the shattering of windows and the injuries can be caused to the humans. The next effect is the thermal effect. Now with the same 15 kiloton, if it is being observed, up to a distance of 2 kilometers, the people are going to suffer with third-degree burns, which can damage the skin and the tissues below it. And there would be no survivor if no immediate medical attention is provided or is received. And we know that if a third-degree burn is there, even if the medical facility is arriving in a timely manner, the probability of survival is very risky. Now let's see what happens between 2 to 2.5 kilometers. The people suffer from second-degree burns, which is normally serious but may not be fatal. And between 2.5 to 3.5 kilometers, people suffer from first-degree burn, such as redness of the skin and the pain that is going to be caused because of the burn. The next one is basically the radiation effect. Now, under the radiation effect, what is happening is ionized radiations are being released. And the ionizing radiation consists of, say, fast-moving neutrons, gamma rays, electrons, or even alpha particles. And these can have a great impact on human body, depending upon which particle and what was the energy of the particle that was incident. Further, if the radiations are going to be absorbed in the soil or the air, what is going to happen is those are going to become radioactive in nature, which can result into that the impact is there for an extended period of time, say for example a few minutes to few years. Now let's see the indirect effect, that is the electromagnetic effect, the first one. Now since whenever an explosion takes place, the ionizing radiations are being released, which results into, say, intense currents and electromagnetic fields being generated. And these are basically referred as electromagnetic pulses. And it can be felt over large distances. And these results into that the electrical grids experience voltage surges far exceeding than those being caused by lightning too, and which will result into the electronic gadgets or electronic equipments getting damaged because of such voltage surges which may take place. And there could be a possibility of, say, total blackout of communication links. The next one is effects on climate. We have already seen that the temperature is going to be huge whenever a nuclear explosion takes place. And that could basically result into large amount of nitrogen oxides to form during the cooling process, which results into depletion of ozone layer in the stratosphere. Apart from this, we have already seen that since the temperature is going to rise within a short span of time, which will result into burning of lot of materials, and so it is obvious that the quantum of oxygen which results into the burning of those materials is going to be less, which in turn resulting into incomplete combustion of those materials, which in turn results into formation of soot. And these soots can act as a blanket. And we know that the earth is able to maintain the temperature because of the solar rays which falls on it. And suppose if the soot remains there for long duration, there could be a temporary period whereby the temperature decreases of that region, and such decrease is basically termed as nuclear winter. If a country plans for weaponization, as such, it may appear to be a simple process, but it is not the case. It has several stages, like the first one, development and production. Then a stage is there which comprises of three sub-stages like delivery system, CQI system, nuclear doctrine and strategy. And the last one is civil defense measures. If we look into the budget allocation, the development and production requires only 7% of the total budget. The maximum budget, 86%, is required for the delivery system, CQI system, and nuclear doctrine and strategy. And the civil defense measure requires only 7% of the total budget. The development and production basically involves the research, which we have already discussed. So now let's look into the delivery system. What happens is the nuclear missile has to be launched from three platforms. One is the land, second is the ocean, that is the sea, and the third one is basically the air. From air, the warplanes can be used up. From the sea, ship or the submarines are being used, whereas from the land, the launchers or the missile launchers are being used. The next one is CQI system. The full form of CQI is Command, Control, Communication and Intelligence System. Whenever a country develops a nuclear weapon, it has, otherwise also, it needs to have a strong intelligence system. And intelligence can be gathered from, say, satellite or using humans, say, spies or other modes. Once such intelligence is gathered or the activities of the enemy country is gathered, it has to be communicated to the appropriate center. And so the communication has to be appropriate and confidential. Once the information is received, appropriate deliberation has to be done. And the appropriate command authority has to give the command to launch the nuclear missile. Once that is being received, the command, the different locations or the stock regions of the nuclear fuels who control the nuclear fuels, they will insert the codes which will result into the launch of the nuclear missile. Now let's look into the civil defense measures. What happens is, as such, if we see, there is no reliable detection mechanism or shooting down of missiles. Just to give an example, during this Russia-Ukraine war also, we have seen that, or we have heard about that the Russia was in a position to basically bypass the air defense mechanism of the Ukraine by using the hypersonic missiles. There could be other mechanisms also, which I need not discuss right now. But then when there is no such reliable mechanism, what is the alternative? See, there is only one mechanism which is considered to be foolproof, and that is to have underground shelters or bunkers. And that's why if you see, say for example, US-Iraq war, the Iraqians had the underground bunkers, and all the countries have created underground bunkers in order to save themselves from the nuclear explosions or other explosion also. The only thing is, these shelters should have sufficient stock of enough food and water, because whenever a nuclear explosion takes place, the impact remains there for certain period, and until unless that gets over, the individuals should not come out. Now let's look into the nuclear doctrine and strategy. It is basically deals with the policy of a nation which possesses the nuclear arsenals, how they are going to use it. India is having a policy of no first use policy, and according to the policy, it will use the nuclear weapon only in retaliation against a nuclear attack on Indian territory or Indian forces anywhere across the globe, because sometimes we do send our forces at different places. The nuclear retaliation to a first strike will be massive and designed to inflict unacceptable damage, because that will only deter the other country from using its own nuclear weapon against India. According to nuclear doctrine, there are a few other things which has to be undertaken, like say building and maintaining credible minimum deterrent. Nuclear retaliatory attacks can only be authorized by the civilian political leadership through the nuclear command authority. The known use of nuclear weapons against non-nuclear weapon states has to be followed. However, in the event of a major attack against India and Indian forces anywhere by biological or chemical weapons, India retains the option of retaliating with nuclear weapons. Then, according to the nuclear doctrine, the continuance of strict controls on export of nuclear and missile-related materials and technologies has to be there. The participation in the Fissile Material Cutoff Treaty negotiations and continued observance of the moratorium on nuclear tests has to be seen. The continued commitment to the global goal of a nuclear weapon-free world through global, verifiable, and non-discriminatory nuclear disarmament is also one of the policy. Now, let's look into whether nuclear tests are necessary for development of a nuclear weapon. No doubt, computer simulations are there, which can also be used up to develop the nuclear weapons. However, at least to get the basic knowledge, the nuclear test has to be conducted. And that's why India did so, Pokhran 1 and Pokhran 2. And I'm sure that you might have heard in Pokhran 1, it was mentioned, Buddha smiled. Now here what happens is, through computer simulation, you can develop the nuclear weapons once you have that basic knowledge for which you have already undertaken a testing. And models can use to create more complicated designs. Now there are different types of tests. The first one, hydrodynamic test. Now this is not banned under the Comprehensive Test Ban Treaty, which is also known as CTBT, because in this the fissile material is not used. In this, an inert material is used with similar properties. Now it is basically used to determine how well the conventional explosives in an implosion design works. I'll be discussing about the Comprehensive Test Ban Treaty later. Now the second test is basically hydronuclear test. This is banned under CTBT. And in this, the actual fissile material is used, but the nuclear yield is kept low. The last one is subcritical test, which is again not banned under the CTBT. Here again, the actual fissile material is used, but the nuclear yield is zero. The material never attains the criticality, and that's why it is not banned under the CTBT. Now, if the test is undertaken, how it can be monitored? Because I'm sure that those who are interested in knowing about the nuclear weapons, they might have read about that when India was planning to undertake the test, it was a total secret. Once the explosion was done, then the countries came to know that yes, the test has been done by India. So if an underground nuclear explosion is being done, it can only be known by the shaking of the ground. And the vibrations of the earth can be detected by seismic stations, which monitor the earthquakes. And the signals which are being generated by a nuclear explosion are different from that of the earthquakes. And so it can be clearly understood. Now let's look into the various organizations which are involved. First, we will look at the national level, and then we go to the international level. The Atomic Energy Commission, which is also known as AEC. It was first set up in August 1948. However, it was set up under the Department of Scientific Research, which was just created in June 1948. The Department of Atomic Energy came into existence on 3rd August 1954. And it was on 1st March 1958 that the Atomic Energy Commission was shifted under the Department of Atomic Energy. The Secretary to the Government of India in the Department of Atomic Energy is ex officio chairman of the Commission. The other members of the AEC are appointed for each calendar year on the recommendation of the chairman AEC and after approval by the Prime Minister. As I have mentioned that the DAE, Department of Atomic Energy, came into existence on 3rd August 1954. The only thing which is to be seen is that it doesn't fall under any ministry. It is under the direct charge of Prime Minister of India. And it has been engaged in the development of nuclear power technology, applications of radiation technologies in the field of agriculture, medicine, industry, and basic research. If we look into the setup, the DAE comprises of 6 research centers, 3 industrial organizations, 5 public sector undertakings, and 3 service organizations. It also has 2 boards for promoting and funding extramural research in nuclear and allied fields, mathematics, and National Institute also, which is the deemed university. The idea of these centers will help in planning out, say, joint research activities. So I'm just giving a brief idea about the organizations. Under the research centers, the first one is the Baba Atomic Research Center, in short BARC, or known as BARC. Indira Gandhi Center for Atomic Research, IGCAR. Raja Ramanna Center for Advanced Technology, RRCAT. The next one is Variable Energy Cyclotron Center, VECC. Then we have Atomic Minerals Directorate for Exploration and Research, AMD. And the last one is Global Center for Nuclear Energy Partnership, GCNEP. Under the industrial organizations, we have Nuclear Fuel Complex, NFC. Then Heavy Water Board is there, which is HWB. And then the last one is Board of Radiation and Isotope Technology, BRIT. Under the public sector undertakings, the first one is Uranium Corporation of India Limited, UCIL. Then we have Electronics Corporation of India Limited, ECIL. And the last one is IREL India Limited, which was earlier known as Indian Rare Earths Limited. Under the power sector, there are two entities, Nuclear Power Corporation of India Limited, NPCIL, and the last one is Bhavini, which is basically Bhartiya Nabikiya Vidyut Nigam Limited. The aided institutions or the other organizations which are there under DAE are Tata Institute of Fundamental Research, TIFR, Saha Institute of Nuclear Physics, SINP, Tata Memorial Center, that is TMC, Harish Chandra Research Institute, HRI, Institute of Physics, IOP, National Institute of Science Education and Research, NISER, Institute of Mathematical Sciences, IMSC, Institute of Plasma Research, IPR, which is there in Gandhinagar itself, Homi Bhabha National Institute, HBNI, Atomic Energy Education Society, AES, Board of Research in Nuclear Sciences, BRNS, National Board for Higher Mathematics, NBHM, University of Mumbai, DAE Center for Excellence in Basic Sciences, CEBS. This diagram, which is there on the screen, highlights about the atomic energy establishments in India, which gives a clear idea that there are many organizations which are basically there working in the field of atomic energy. Now, the next one, which I need to share, is about the Atomic Energy Regulatory Board. This was constituted in exercise of the powers conferred by Section 27 of the Atomic Energy Act 1962. Now, this basically lays down the powers with the board to ensure the safety standards and frame rules and regulations regarding to the regulatory and safety requirements envisaged under Section 16, 17, and 23 of the Atomic Energy Act 1962. The AERB has the powers of the competent authority to enforce the rules and regulations framed under the Atomic Energy Act 1962 for radiation safety in the country. It is also basically the authority to administer the provisions of the Factories Act 1948, the industrial safety for the units of DAE as per Section 23 of the Atomic Energy Act 1962. These were mainly looking for the peaceful purposes. Now let's look into the weaponic condition. The Cabinet Committee on Security is basically the umbrella body which looks into the security aspect, and it comprises of the Prime Minister of India, Minister of Defense, Minister of Home Affairs, Minister of Finance, and Minister of External Affairs. Now let's look into specifically the nuclear weapons. It is basically falling under the Nuclear Command Authority, which comprises of two setups, Political Council and Executive Council. The Political Council is chaired by the Prime Minister of India, and it is the sole body which can authorize the use of nuclear weapons. The Executive Council is chaired by the National Security Advisor. It provides inputs for decision making by the Nuclear Command Authority and executes the directives given to it by the Political Council. Now let's go to the international arena. We have International Atomic Energy Agency, IAEA, which is also known as the world's Atoms for Peace and Development Organization. It is the international center for cooperation in the nuclear field. This works with its member states and multiple partners worldwide to promote the safe, secure, and peaceful uses of nuclear technologies. The statute of IAEA was approved in the year 1956 on 23rd October and came into force on 29 July 1957. The statute has been amended 3 times after that. The IAEA was created in response to the deep fears and expectations generated by the discoveries and diverse uses of nuclear technology. The genesis was basically the US President's Atoms for Peace address to the General Assembly of the United Nations on 8th December 1953. And there are 173 member states. The headquarters of IAEA is situated in Vienna, Austria. The regional offices are Toronto, Canada since 1979 and Tokyo, Japan since 1984. There are licensing offices also. One is in New York, USA since 1957, then in Geneva, Switzerland since 1965. The agency-run laboratories are in Vienna and Sibersdorf, Austria since 1961 and Monaco since 1961. The next organization or the group is basically Nuclear Supplies Group. It was created after the explosion in 1974 by a non-nuclear weapon state, and I'm sure that all of you know which state that is, which basically demonstrated that nuclear technology transferred for peaceful purposes could also be used to develop nuclear weapons. It is basically a group of nuclear supplier countries that seeks to contribute to the non-proliferation of nuclear weapons through the implementation of two sets of guidelines for nuclear exports and nuclear related exports. The guidelines basically contain the non-proliferation principle adopted in the year 1994, whereby the supplier, notwithstanding other provisions in the NSG guidelines, authorizes a transfer only when satisfied that the transfer would not contribute to the proliferation of nuclear weapons. If we look into the guidelines, they are consistent with and complement several treaties, like Treaty on the Non-Proliferation of Nuclear Weapons (NPT), Treaty for the Prohibition of Nuclear Weapons in the Latin America, the South Pacific Nuclear Free Zone Treaty, the African Nuclear Weapon Free Zone Treaty, the Treaty on the South East Asia Nuclear Weapon Free Zone Treaty, and the last one, the Central Asian Nuclear Weapon Free Zone Treaty. Each treaties are also known from the place where the treaty was signed. The NSG guidelines are implemented by each participating government in accordance with its national laws and practices. Decisions on export applications are taken at the national level in accordance with the national export licensing requirements. And there are currently 48 participating governments in the NSG. Now let's look into the national legal hierarchy. This is basically a general structure which has been given. The first level is constitutional level. It establishes the basic institutional and legal structure governing all relationships in the state. The second level is basically statutory level. Under this, the specific laws are enacted by a parliament in order to establish other necessary bodies and to adopt measures relating to the broad range of activities affecting the national interests. The third level is basically the regulations, where highly technical rules are being framed. And the fourth level, which is basically the non-mandatory guidance requirement in instruments, this deals with recommendations designed to assist persons or organizations in meeting the legal requirements. Now let's look into the principles of the nuclear law. The first principle is safety principle. Since the nuclear is dealing with radioactive substances, the safety of the people working there, the safety of the individuals staying in the vicinity is of utmost importance. And so the first principle is the safety principle. Security principle. We know that the radioactive technology, the nuclear technology, can be misused by the antisocial elements. And so the security of the reactor where the nuclear technology is being used has to be ensured at any cost. Even the weapons which are being developed has to be secured. So that is the second principle. Responsibility principle. The people who are there have to act responsibly while dealing with the nuclear technology, because any small mistake can result into havoc. And so it has to be ensured. Permission principle. Since whenever a technology is being used up, say the nuclear activity is being undertaken, it is not just a single party which is involved. There could be several parties, and there could be even certain private parties, like say for example excavation. It could be given, a license can be given to another party. No doubt in India that is not the scenario. So that is not going to be a complication. But yes, the permission has to be looked into whether, and each year there should be a review of the activity, how it has been undertaken. But say private parties are there by transporting the material. So those things has to be looked into. Continuous control principle. There has to be constant review to ensure that there is a strict control over the whole procedure or the process of the utilization of the nuclear fuel. Compensation principle. There is always a probability of certain accidents. Like say, for example, even if accident is not there, exposure to nuclear radiation. And so the appropriate compensation principle has to be incorporated within the nuclear law. Sustainable development principle. You all know that the sustainable development goals has been adopted by the United Nations. And nuclear technology can help out in the achievement of the sustainable development goal. So that principle has to be appropriately reflected. Compliance principle. See, the rules can be framed, the laws can be framed. However, it has to be ensured that there is a strict compliance of the laws, because else it is not going to be of any use. So if someone violates it, what are going to be the punitive actions also has to be reflected. Independence principle. What happens is there will be certain bodies which may be involved in the generation of or utilization of the nuclear materials. There will be certain bodies which will be keeping a watch how the activities are being undertaken, like say watchdogs. Now these has to be independent. Else what will happen is the conflict of interest will be there and the true things may not come out. So independence has to be there. That is the independence principle. The next one is transparency principle. We know that, we have already seen that the nuclear technology can be used for two purposes. One is peaceful and the other one is weapon purpose. And so there has to be a transparency. And the nuclear law should have in it this particular principle. Like say, for example, I'm sure that you might have heard of the constant request being raised to inspect certain reactors of certain countries by other countries to know whether the nuclear technology is being used only for peaceful purpose or not. I am not naming the countries, but I'm sure that all of you know. And the inspection which is being requested is by IAEA, by that country. And the last one is international cooperation principle, which stresses on nuclear energy technology is for benefit of all. Till the extent it can be possible, each country should help the other country to enable them use this technology so that everyone is at benefit. Now, international regulatory regime on nuclear waste. IAEA's 1990 Code of Practice on the Transboundary Movement of Radioactive Waste is the first one. It is non-binding in nature and it was adopted by the UN and other international organizations. It basically fills a gap in the Basel Convention on controlling transboundary movement of hazardous waste, 1989, because it didn't deal with the radioactive waste. This has two basic principles. The first one is states should take appropriate steps necessary to ensure that radioactive waste within its territory or jurisdiction is safely managed and disposed of to ensure the protection of human health and environment. And the second is states should take appropriate steps necessary to minimize the amount of radioactive waste. The second one is basically Joint Convention on the Safety of Spent Fuel and Radioactive Waste Management 1997. It came into force in 2001. It applies both to radioactive waste disposal and to spent fuel management. India is not a party to this convention. There are few others which are basically dealing with safety and security of nuclear installations. The first one is Convention on Nuclear Safety, 1994. It was enforced on 24 October 1996. It came into force on this date. The Convention on the Physical Protection of Nuclear Material, 1980. It came into force on 8 February 1987. UN Security Council Resolution 1540 on Nuclear Terrorism, 2004. Convention for the suppression of acts of nuclear terrorism 2005. This one came into force in July 2007. ILO Convention number 115 concerning the protection of workers against ionizing radiations 1960. Additional protocols of the Geneva Convention of 1949 on armed conflicts. IAEA safety guides. I'm not describing all this. I'm just giving the names so that one has an idea about the legal regime. The next one is regulatory issues in decommissioning. Decommissioning process as such is not an easy task. It requires good number of planning. And that's why the first issue is decommissioning planning. Because there are different methods by which a plant can be decommissioned. The next one is facility shutdown activities. Once the plan is being made, the activity has to be undertaken. The activity has to be undertaken in line with the plan that has been made. And if a deviation is there, you need to have the alternate mechanism which can be used up to ensure that things are under control. Radiation protection, safety, and security has to be ensured. The waste has to be managed appropriately, and that is the next issue. The cost factor. What happens is, whenever decommissioning is going to take place, there has to be a cost factor, but within the limit. Because if a plan is being made which is going to incur huge cost, I'm sure that many may avoid doing so. And the last one is remediation measures. One thing which is of importance is that whenever decommissioning of a reactor is being done, it varies with reactor type, size and age, and the method of decommissioning chosen. And so it will have a great impact. So it has to be taken into consideration. Now let's look into the laws which are there at national level dealing with the atomic energy. Atomic Energy Act 1962, which is basically the umbrella or act law, applicable to the energy released from atomic nuclei as a result of any process, including the fission-fusion processes, minerals, equipment, and radiation. The next one is Atomic Energy Arbitration Procedure Rules 1983. Atomic Energy Working of the Mines, Minerals, and Handling of Prescribed Substances Rules 1984. Atomic Energy Safe Disposal of Radioactive Waste Rules 1987, which deals with the safe disposal of radioactive waste. Then we have Atomic Energy Factories Rules 1996. We have Atomic Energy Radiation Protection Rules 2004, which mainly focuses on the protection from the radiation which are being released. Then we have Civil Liability of Nuclear Damage Act 2010 and the rule which was framed under the Act, Civil Liability of Nuclear Damage Rules 2011. This basically deals with the liability factor. Then we have Guidelines for Cooperation with other countries regarding peaceful uses of atomic energy 2010. Then we also have Atomic Energy Radiation Processing of Food and Allied Products Rules 2012, because we know that the atomic energy, that is the radiation, can be used up for other purposes also. Nuclear Liability Fund Rules 2015, how the fund has to be used and appropriately discharged. For that, the rules have been laid down. Schedule of Prescribed Substances under Atomic Energy Act 2016. And then we have the Guidelines for Nuclear Transfers, Exports 2016, which deals with export of the nuclear technology or the material. Though India has not been doing so, then let's look into the international regulatory framework. But this is mainly dealing with the nuclear weapons. The first one is Non-Proliferation Treaty, NPT. This was negotiated in the year 1968, became effective in 1970, and the number of parties are 191 and the number of signatory parties are 93. India is not a signatory. According to this, the countries which manufactured and exploded a nuclear weapon or other nuclear explosive device prior to January 1, 1967 are only considered as a nuclear weapon states. And that is the reason, though India has a nuclear weapon, it is not considered as a nuclear weapon state. The key principle of this treaty is that the countries which are in possession of nuclear weapons should only have those weapons. It should be limited to them. And to ensure this, what they have to do is they should not be transferring the nuclear weapon capability to those countries which doesn't have. The next one is the Comprehensive Test Ban Treaty, CTBT. This was concluded in the year 1996. However, this comes into force only when all the countries which have the nuclear capabilities sign the treaty, and India is not a signatory, and so it cannot come into force. The signatory states are 185, and the ratifying states are around 172 in number, and the non-signatory states are 11, in which India is one of the countries. The next two states, which are basically the nuclear capable states, the signatory states are 41, the ratifying states are basically 36, and the non-signatory states are 3 in number. The main purpose of this is to put an end to nuclear explosions, which seek to test weapons technology. Now, the signatories of this treaty cannot conduct the nuclear explosions, and India, Pokhran 1 and Pokhran 2 were conducted later, and without the conduct of that, India could not have developed the nuclear weapons, and so India is not a signatory to this. It bans only explosions. That is the difficulty, which we have already seen. It allows the subcritical non-explosive weapon tests and the computer simulations. The next is basically the fissile material cutoff treaty. It seeks to put an end to the production of fissile material, which could be used for the production of nuclear weapons. Now, production can be checked only by physically entering into the sites, and that's why certain country is requesting that IAEA should be allowed to inspect the nuclear reactor of certain countries to know where the material is being used. Now, here what is happening is those nations joined the Nuclear Non-Proliferation Treaty as non-weapon states are already prohibited from producing or acquiring the fissile material for weapons. Now, the FMCT would provide new restrictions on the 5 nuclear weapon states that are United States, Russia, United Kingdom, France, and China, and the 4 nations which are non-NPT members like Israel, India, Pakistan, and North Korea. Now let's look into the international agreement which India has signed, 123 agreement with the US. Now this is basically an agreement which refers to section 123 of the US Atomic Energy Act. There is a ban on transfer of nuclear technology to other countries under this act. And so the Hyde Act was passed by USA to make an exception for India, because India is not a signatory to the Non-Proliferation Treaty, to enable transfer of technology for civil nuclear energy purposes. The 123 agreement is the terms of engagement which operationalizes the treaty agreement between India and USA for transfer of civil nuclear technology. However, to undertake this, one of the requirements is that the nuclear reactors which will be set up under this agreement has to be allowed to be inspected by the IAEA. And secondly, India should also become a party to Nuclear Suppliers Group, wherein one of the conditions is that the Nuclear Non-Proliferation Treaty has to be signed by India. There also an exception is being thought of or has been requested, and I'm sure that all of you might have heard of that China has been objecting to India's party to the NSG because of non-signing of the Non-Proliferation Treaty. That is no exemption being created to be part of the Nuclear Suppliers Group. By this, I come to the end of the talk. I hope this talk had been helpful, and I'll be happy to receive any queries in this regard. Thank you very much. It was my pleasure to place before you this talk. Thank you very much.